All right, here we are. I've already done a video for number 2. You can take a look at that. I took a long time and did a good job on number 2. I'll go a little faster here on these other ones. They're a little bit easier ones. Number 1, can the acceleration be different direction than velocity? Of course, because if it's slowing down, that's exactly what happens. You have a velocity going in one direction, and you have the acceleration going in the opposite direction, and then you're going to have slowing down. So if, say, the velocity is positive and the acceleration is negative, you're going to have slowing down, or vice versa. However, if they're both negative, you're going to be speeding up in a negative direction. If they're both positive, you're going to be speeding up in a positive direction. So they're completely different things. Acceleration is the change in the velocity. That's why we have units of meters per second per second. So they're just very different things, and they can be in totally different directions. Like I said, 2's on a different video. 3, I kind of cheated a little bit here, and we used Excel. But in any case, you should get around 50. If you're doing it without Excel, you'd have to do some actual slope. Let's say you took these 4 numbers. You could take the change in velocity, figure that number out, get the change in time, subtract those 2 numbers to get that. You could divide those numbers. You'd get a number around 49. Won't be exact. Then you could say use these 4 numbers and do the same thing, delta y over delta x. Then again with these 4, same thing again. You could do, change in velocity, figure that number out, change in time, figure that number out, divide them. So you could get 3 different numbers, average them. You'll get somewhere around there. It won't be the exact because Excel has its own little process. But the point here is that acceleration is change in velocity, so it's the slope on a velocity time graph. Okay. For number 4, I picked using the tenth. I have at the tenths accuracy here for sig figs. This one's also at the tenths, so my answer needs to be at the tenths. That's what matters when you're adding. When you're adding, you want to look at decimal place. This is at the tenths, this is at the tenths, that's at the tenths. So it's been done correctly. And then we don't count when we're adding, but if we did, this is 3 sig figs, this is 2 sig figs, and that's 4 sig figs as was asked. I'm going to slow down, do a little better job with this problem here. This is precision versus accuracy, which sound like the same number, and when we use them in English, we also, we just don't really think about them being different words, but they're actually different words. So accuracy versus precision. So the pictures here are someone shooting a gun from a long distance. Let's say they have a scope on the gun. And let's look at this one first when there's neither air, so we have accuracy and precision. And look at this. This is someone who's a very good marksman. They're really good at shooting the gun. They can hold the gun steady. And they have equipment that's really good. The scope, it points exactly where it's supposed to. The gun shoots where the scope is looking. And sure enough, this excellent marksman with this great equipment gets exactly what they're supposed to get. That is accurate and precise. There's neither air. If we imagine with this example here that we have the same great marksman, the target's so far away they can't even see where they're hitting, but the scope is off. Like the scope is actually pointing somewhere where it's not supposed to. So the marksman assumes they're hitting the target, and actually they just shoot four bullets really quickly, boom, 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 boom. They think they're all going to hit the target. But when they look carefully, they realize they missed. But that's because the equipment was off. And that would be an example of a systematic error. Here we have not being accurate, right? Because the average is way over here. But it's still precise. And so there still is validity to the data. It's precise. So precision has to do with getting the same number every time. Accuracy has to do with getting the right number. Which brings us over to this one here. With this one, we've got accuracy, but no precision. So this would be the same great equipment that was being used, but you know what? I'm shooting the rifle, and I don't know anything about shooting rifles, so I just got lucky to hit the target at all, and I'm just all over the place because I'm not very good at that. So that would be accurate because I know to try to aim at the target, and if I average these, I get the right value, but it's not precise, okay, because the numbers are not close to each other. If I go here, this would be the worst. This is, I'm shooting again, so I'm not very accurate. But the precision's also off because we're using the gun where the sight's not working properly. So that would be this one, and this would be the worst data that we could get. This is obviously the best. This has both systematic and random error. This has only random error, but there's no systematic error. And here we have systematic error. Let me do this with numbers. Here's a huge data set. Okay, this data set is big, and we're looking at this data set. And if we asked ourselves, okay, if the right number was supposed to be 2, look at this. We all have all pretty much the right answers, a couple off by a little bit. But this is darn good data. We'd call this both accurate and precise. However, if the right answer was 7, okay, the right answer was 7, then if we look at this, this is not very good data all of a sudden, but it still is precise because we keep getting the same values, which means precision. It's not the right answer, so that's why it would be not accurate. That would be this analogy here. Let's say the right answer was 7, but the data that I got when I went to do the problem was something like a 1, and then I got a 13, which isn't very good. Let's say then I got, I don't know, 4, which isn't too bad, but then I got a 10. I don't know, and then I did it again. I'm like, wow, this really isn't very good, and I got a 3, and then I get, say, an 11, and I'm like, wow, this data is all over the place, not very good. But I went to average it and said to myself, okay, well, I'm going to go ahead and average up this data and see how it got. So I go 1 plus, try to do this fast here, 1 plus 13 plus 4 plus 10 plus 3 plus 11. And there's how many pieces of data there? Looks like there's 6 pieces of data. And sure enough, I get 7, which I don't know if you remember, but we were saying 7 was the right answer. So this is really bad data in that it's not precise because I keep getting different numbers. But if I take the average, I got a number that's right on the correct answer of 7. And so sure enough, it has some validity. There's something going on there. So we call that random error. Okay, random error, but there'd be no systematic error since the average was right on. Finally, if you just have really bad numbers, let's say I had back here a 1, a 2, you know, a 4, maybe I got up and had a negative, had a 1.5, say, or just some really bad, but all the numbers were too small, so I got a 1. So the right answer is supposed to be 7, and I'm getting these numbers, but they're jumping all over the place also. That would be both systematic and random error. So I hope that helps a little bit with this one. It's also important for lab write-ups. So you might want to watch this video also before you write up your next write-up. Okay, thanks.